Look at binomial expansion using Pascal's triangle. I made a video on the Pascal's triangle in the previous video, but to summarize, Pascal's triangle is basically this. So the outer edge of the triangle is always lined with ones, and the number below the numbers is the sum of the numbers that's above it. So if I just finish making this, I'll make it to the 5th row. Like so. The outer edge of the triangle, so these numbers and these numbers, they're always going to be ones, so the triangle is lined up with ones. And this tells you the row number. So this one is row 0, row 1, row 2, row 3, row 4, row 5. And how do you find out Pascal's triangle? So once you just have this basic 1, 1, 1 triangle made, then the number that comes below it is just the sum of the two numbers that come above it. So 1 plus 1 makes 2, that's why it's 2. And then this 3 comes from 1 plus 2, that's 3. 2 plus 1, that's 3. And then this 4 comes from 3 plus 1, 4. 3 plus 3, 6. 3 plus 1, 4. Then 4 plus 1 makes 5, 6 plus 4, and you get the point, right? And then the outer edge is just ones. So Pascal's triangle is just a continuously expanding infinite triangle of just the numbers that came before it. Now we're going to use this to solve binomial expansions. So binomial expansion is just an easy way to expand binomials. So in case you didn't know, binomials are just expressions with two brackets in them. So if you have a plus b, you have two terms within it, right? And then if you have this to the nth power, this is a binomial. You have two terms within the brackets and you're trying to expand it into its full form. Now n squared or n cubed, up to here, I'd say it's pretty easy. You can do it using the multiplication method. Once it becomes like n is 7, n can even become like 10, 15. That's when you really want to use binomials, because it really speeds up the process a lot than just multiplying each of the brackets one by one. You really don't want to be doing that, do you? So it's just an easy way to expand brackets really quickly. So let's take a little bit of an example, right? Okay, so if we have the equation a plus b to the power of n, we can use binomials because this n over here, it tells us the row that we're going to use. So as aforementioned, this is row 1, right? Sorry, not row 1, this is row 0. That's a really common mistake people make. That's row 0. That's going to be row 1, row 2, row 3, row 4, and so on. Because you look at the second number and it tells you the row number. If there's no second number, it's going to be 0, isn't it? 1, 2, 3, 4, 5. That tells you the row number. Now this nth power, the power that's after the brackets, tells you which row to use. So for example, if the number was a to the b to the power of 4, we'd use the 4th row binomials. Then how exactly do we use this to solve our expression? Well, let's try solve it. A plus b to the power of 4. We know it's 4, so we know we're going to be using the 4th row of binomials. And the fourth row of binomials is 1, 4. Okay, let me go one by one. 1 first. Then we put our a inside, and that's going to be to the power of 4. Then we put our b, so our terms, and then it's going to be to the power of 0. I'll explain this in just a second. We're going to add that with the second binomial, 4. And then we're going to have a to the power of 3 and b to the power of 1. We're going to add that. Next digit in the 4th row, 6. 6. And that's going to multiply with a to the power of 2 and b to the power of 2 as well. Hopefully you're... Okay, let me just make a bit more room there. Hopefully you're noticing a bit of a pattern. We're going to have the next digit. It's going to be a 4. And then we're going to have our a. This time a is going to be 1. And our b is going to be 3. Write that a bit clearer. And our last digit, our 1. And that's going to multiply with a. Let me write that a bit better. 1 multiplied by a to the power of 0. And b to the power of 4. Hopefully you kind of see the pattern from me doing this. So this coefficient, not the coefficient, sorry, the exponent, so the indice, the power. So this exponent tells you what the number that comes in front, that's called the coefficient, tells you what the coefficient is going to be. So this 4 tells us to use the exponent of 4, tells us to use row 4 of Pascal's triangle, and then the numbers in the Pascal's triangle tells us what the exponent of all our expression is going to be. First one's going to be 1, 4, 6, 4, and 1, as seen in the Pascal's triangle. And then we add a, our a term, and then our b term. And then the powers can get a bit confusing, but I'll try to explain it as simple of a way possible. We have 4 and 0 first. Because our exponent is 4, the first term is going to be 4 to the power of 4, and b, the second term, is going to be raised to the power of 0. Then here, this decreases by 1 to become 3, and this increases by 1 to become 1. Then this one decreases by 1 again to become 2, increases to become 2, this one decreases, this one increases, decreases, increases. But what you'll notice with each of them is that the 2 add up to make our exponent of 4. Same here. They will always add up. So they just take turns. One increases, one decreases, until all of them have had their share of the numbers. So if it's raised to the power of 4, every number will have everything from 0 to 4, sorry. And if it's raised to the power of 7, then we'll have to do it 7 times with 4, 1, 2, 3, 0, 1, 2, 3, 4, 5, 6, 7. But the exponents add up to 4, the exponents of each of the terms will add up to this one. And then one increases and one decreases to make our final answer. And now all we have left to do is just simplify our expression. So if we take a look, 1 times a, first of all, let's simplify it. B to the power of 0, remember, anything to the power of 0 is 1. So if this becomes 1, 1 times 1 is 1 times something is just going to stay the same, right? So we can just basically cancel anything to the power of 0 out. And if you've done it correctly, you should only get 0 2 times. Okay, so we canceled our 2 zeros just to make our life a little easier. So the equal sign, 1 times a to the power of 4. Well, that's just going to be 1a4, right? I'll just simplify the simplify the 1 and just get rid of it. So a to the power of 4 plus 4 times a cubed plus 4 times a cubed multiplied by b to the power of 1. Well, that's just going to be 4a cubed and b to the power of 1, which we simplify to just be that, 4a cubed b1. And then we have our next term. Well, 6 times a squared plus b squared. Well, that's just going to be 6a squared multiplied by b squared. And then our next one, 4 times a squared, this one's to the power of 1, by the way, so it's going to stay the same, 4ab cubed. And lastly, this one was simplified, we don't need it, so it just becomes 1 times b to the power of 4. That's just going to become b to the power of 4. Is there anything we can simplify? No, there are no and nothing similar. So this will be our final answer for a plus b to the power of 4. Let's take a look at another example. That was the easiest example of binomial expansion there possibly can and will be. So let's take a look at something that's a bit more challenging. Something like, say, p minus 5 cubed. Let's draw our Pascal's triangle again, 1, 1, and then this one will be the sum of the above, so 1, 2, 1, 1, sum of above, 3, sum of above, 3, and then lined with 1s, and we have our exponent being a 3. So we know we're going to use the third row, don't need to really continue drawing it from there, because we already have the third row. Then what do? We're going to make our equation. So we know we're using this row of Pascal's triangle, the third row, because our exponent here is 3. So we can have 1 times p to the power of 3 times negative 5 to the power of 0 added to next term in Pascal, 3 multiplied by p, this decreases by 1, so 2 multiplied by negative 5 increases by 1, 1 plus next term 3, p decreases by 1, so it's going to become 1, and then negative 5 is going to increase by 1, so it's going to become 2, and our last term should be 1 multiplied by p to the power of 0 and negative 5 to the power of 3. And you'll notice all the exponents in each term add up to make 3. That means we've done it correctly. And all we have left is to simplify. So 1 times p cubed. First of all, let's get rid of the zeros, because it's just going to become 1, and we don't want it. And then we just do 1 times p to the power of cubed, so p cubed plus 3p squared minus 5 to the power of 1. Well, let's multiply minus 5 by p first. So this is going to be minus 5p squared, right? Minus 5 times by 3 is minus 15. It's going to be not going to be a plus. It's going to be minus 15p squared. You want to be really careful with these binomials when you're expanding them, because they can really get quite... you can mistake them quite easily. That's all I want to say. Minus 15p squared. And then we have our next term. We have our minus 5 squared. So this is going to, if minus 5 is squared, it's going to become minus 5 times minus 5, which is going to be 25, right? Positive, because minus and a minus makes it positive. We're multiplying that by 3, so that's going to become 75p. Just watch out for your negatives, that's all I'm saying. And then our last one, 1 times negative 5 cubed. Well, that's going to be negative 5 times negative 5 times negative 5, right? Well, that's going to make 25. And then that's going to make multiplied by 5, so it's going to give us negative 125. And there's no p because the p cancelled out. Yeah, that's it. Hope this explains binomials. Thank you for watching.